I'm delighted to be here. This is my third presentation in 4 years at this conference, and I think it's always great to go to multidisciplinary conferences like this where we all share interest in a common method around Bayesian networks, but I always learn a lot from my colleagues working in other disciplines, so it's great to be here. I'm going to talk a bit about the setting and where I do this work, and a little bit about the problem that I'll be talking about today, and then an outline of how the analysis developed and provide some results from this analysis, and then I'd like to do a preview of what I'd like to be talking about at next year's conference. I'm all thinking ahead. So first of all, the area that I'm talking about today is this area in northwestern Canada. I'm a biologist by training, and this is where I do some of my work in this particular area. I don't live here because I'd like to stay married, so I live down here instead because it's quite a harsh landscape. It's beautiful. I love it. This area is about 100,000 square kilometers, so it gives you a sense of the scale of the area that we're talking about. It's an area that's dominated. I don't have a microphone on. So oh, sorry. Where did we just realize that?
Maps in the summertime, right?
Yeah, that's right. Google Earth in the summertime.
Really?
Yeah, it's there. Oh, it's here. Sorry. That's okay. I just realized that. So this is an area, this is just a small area of this vast portion of subarctic Canada, which is what we call the boreal forest, which runs right from Alaska, which isn't part of Canada. It should be, but it isn't. There's Alaska and runs right across the country, right over to Newfoundland in the east, which is actually, this is closer to Paris than where I live, actually. This is closer to Paris than where I live is to Newfoundland, so it's huge distances we're talking about. A lot of this low-lying muskeg, what we call muskeg, so low-lying boggy habitat with short little trees. There's a researcher standing here, so it gives you kind of the scale. These trees are hundreds of years old. They grow very slowly, not just because it's very cold, but because it's a very nutrient-poor, poorly graded area. Long distances between small communities. So the communities here, mostly indigenous, so the Dene people, towns ranging from a few hundred people to a few thousand people, separated by some paved but many dirt roads of hundreds of kilometers between these towns. So I was laughing at a hospital every 10 kilometers in Belgium. I think there's one hospital at 100,000 kilometers here, and the odd nursing station to fly the emergency cases out. And as I said, short, long winters, short but surprisingly warm summers. So that's the kind of area that I'm working in. And the species that I'm talking about, caribou. Caribou are simply a North American version of reindeer. They're all the same species, and they have a circumpolar distribution, so right around the globe. You might think of caribou and reindeer as species that live in large herds in the far north in the tundra. The Sami people of Scandinavia, of course, herd reindeer in that kind of area. But this actual subspecies is called woodland caribou, and they range right down into wooded areas of Canada. So they range a little farther south, and they occur in much smaller groups. So yes, I have to show my requisite video of how we study sound effects. The big antlers here are the males, and the ones with the small It's that as well.
Muted?
Ah,
It was muted. Okay, right. These are the males, these are the females. And so when we get the caribou on the ground, there's a tremendous amount of processing we do when we have them there, because obviously it's very expensive. Running these capture crews costs thousands of dollars an hour to run, highly technical, highly specialized, very dangerous, very remote. And helicopters burn a lot of fuel, but they don't carry a lot of fuel because of weight, so we have to have the logistics around remote caches for fuel. Obviously, if there's any safety issues, like I said, one hospital, over 100,000 square kilometers. So the animals are quite calm once you get a blindfold on them, because they've never been blindfolded at all, so they don't really know what's going on, so you just kind of do a lot of processing. This woman, you can't tell she's a woman, but she's a woman, drawing blood there with the gloves on. Her husband, by his positioning, I would say he's probably getting a rectal temperature on the animal there. And we also have some equipment to measure fat, non-invasive ways of measuring fat content through conductance. So that's the machinery that's going on there. But the main thing we do is we want to attach radio collars. You can see a little radio collar there. I've got another quick video here of just the release. They hobble the hooves so that so they don't kick. So you can just see them releasing the hooves off here, like releasing the hobble. And they're also, when they take the blindfold off, this is actually in the Rocky Mountains. This isn't out in the area where I'm talking about today. But there's a good view of the radio collar there with the antenna. And you see she's not particularly traumatized by this. She just kind of walks away. So once she's released, this radio collar triangulates a position based on GPS twice a day, and then uploads. There's a satellite uplink. It sends that location to the servers of our satellite company, our collar company in Germany, who then email the locations back to us. And so it's all completely automated now, which is a tremendous benefit over what it used to be. It was a lot more complicated. You had to do everything either by the ground or from the air. So satellites have really changed things. And as a result of that, we can collect a large number of locations in a fairly short time. And my colleagues and I were lucky enough to assemble this tremendous data set collected from 1,226 caribou over 25 years. And there's more than 1.3 million data points on this particular graph, so a very large number of locations. And the specific question that I'm talking about today is about spatial structuring. So we have this distribution of points, and the question to ask is this, there's obviously some discontinuity in the distribution. We have this group down here, but the question is this one big population, or is it more than one population? Because if we have distinct populations in this area, they may require different kinds of management actions in order to affect recovery. Caribou are not doing well, and so we have to, there's a lot of effort going on right now to try to improve their status. And so we need to know if this is a discrete population or if there's discrete populations in there. And it's not very easy to figure out. So this is another view. We often draw home range polygons. So we have these points, and then we basically join the dots around the outside of the points to produce these polygons. And you can see that the home ranges are overlapping, and we have animals moving from here to here and from here to here. So at what point you say, well, okay, actually this is going to be a discrete population and this one isn't. And so that's what I was faced with. And this has been done in the past, mostly through expert opinion and in ways that don't make a lot of sense. So these green areas separated with all this orange line work, this was how, to date, we're separating these populations out. But you can see they're following jurisdictional boundaries here. So this is the 60th parallel. And there's no fence, there's no road, there's nothing to stop. Obviously, animals are moving back and forth, so some of these lines don't make any sense. So my question was, okay, can we do a better job with all these data of having a quantitative way of establishing whether or not this is one big population or 5 populations or 50? How could we do that? And there has been some quantitative work done on this before. So this is, for instance, movements of polar bears. So this is in the far north here. These are walk lines between different polar bear locations. Huge area. My 100,000 square kilometer study area is a little tiny postage stamp down here. So this is a vast area up here. And what they did is they did a clustering analysis on median seasonal locations. So they would take the median location in the x direction, the median location in the y direction for each polar bear for each season. So they basically had 8 explanatory variables, and then they would cluster on that. And it's not a bad method, but they're clustering on the medians. So essentially, they're throwing out a lot of data. You can get a lot of over smoothing when that happens. And so I thought it was quite unsatisfactory to have all this tremendous spatial information, but end up throwing it all out and doing your analysis on medians. But at the same time, it's very difficult to cluster on a very large number of locations because the matrices become intractably large. So I was discussing this issue with Stefan last year at the national conference and explained to him this data set that I was starting to put together. And so he said, well, I'll think about it. And so eventually we connected in November. It was not easy because Stefan was doing another one of his worldwide tours, spreading the gospel of the BayesiaLab. And but we did connect. It was on a hot and humid Saturday morning in Singapore for him, and for me it was a dark and stormy Friday night in the Vancouver airport while I was trying to get home for the weekend. But he had this idea, and he said, and the way he was looking at it, he basically flipped my thinking, because what I had been thinking about is thinking about, okay, so I have all of these locations as my observations. Basically I have all these caribou as my observations, and I have my their locations in coordinate space as my variables. I have an x variable and a y variable, and then I have all these caribou observations. But he suggested, well, why don't you flip this the other way, essentially, and look at it such that all the caribou are the variables, and their locations in space are the observations. So I thought about that for a while, and what I did is I ended up assembling the data this way. This is an example of a part of my study area where each one of the colors associated on this particular diagram, those are different caribou. And then I superimposed a 10-kilometer square grid on top. And I counted, within each one of these squares, I counted the number of locations for each one of the caribou, and that became my data set. So when I brought that into BayesiaLab, what essentially I had was all of my grid locations. This is the identifier for my grid locations in observations. And then I had each caribou as a variable. And within each cell was the number of locations that were occurring for each caribou within this observation. So the data set I had were 1,226 variables in the columns and 2,356 observations. If there were zeros across all of the observations, so basically no locations in those cells, I threw those out. They're not providing any information. But if they had any numbers in them, I kept them in. Now, the thing is, there's still a lot of zeros. So this is and the reason for that, of course, is because over this vast study area, any one caribou is only going to be living in a few cells. And so for the vast majority for a caribou, for a given location, it's going to be empty. And I'll return to that issue in a bit. So we have this distribution where we have piles of zeros and then a few locations, but in some squares we might get hundreds or even thousands of individual locations. So I had to use a very simple discretization to keep the number of classes, and I tried a few different things. I used the unsupervised multivariate routine just to have BayesiaLab pick my class cutoffs. I also just used binary, either no locations or locations, and then I went up from there and tried a few different ones. And then, of course, to start learning the network, this is an unsupervised problem because there's no target node. I was simply looking at the relation. I wanted to know the relationships between caribou based on their locations in space. And so I simply I started with a maximum weight spanning tree. So each one of these nodes is an individual caribou. So there's 1,226 nodes on this graph. And then obviously the more closely related caribou are going to show up together on the graph. So this is what I've termed the social graph. So this is the caribou social graph, which shows how animals on the landscape are starting to cluster up. And there are a couple of things to take away from this. First of all, it's not a fully connected network. So there are places, this obviously is a separate cluster here, and it's coming up here, and then the big one up here. And so it's not fully connected just using the default parameters. And the other thing too is that there's a whole bunch of caribou that don't cluster up at all. And so those are animals for which we don't have a lot of data, for instance. So they didn't live very long after we collared them, or their collars failed, or for whatever reason. So there's not enough information for them to be included in the network. But that was the starting point for me. Now, the great advantage of using a maximum weight spanning tree, obviously, is it's very fast. You can learn the network very quickly. The only downside is that it is a true tree, so you may be missing. There may be an opportunity to improve fit by allowing more connections amongst the animals. So I did try some other learning routines. As it turns out, the Soplec routine was actually the one that I could generate a network in a reasonable amount of time. A lot of the other ones took too long, and I pay by the hour, so I can't afford to use some of these learning techniques. So, but as you can see, if you zoom in on here, a lot more connectedness. So you're building more relationships amongst the animals, so that you can connect them all. There's multiple connections going on. So that's one of the advantages. One of the disadvantages of using this is that it's more difficult to explain that routine to mere mortals as opposed to a maximum weight spanning tree, which is a lot more intuitive for non-technical people to understand. And so we tried a couple of different things, and when I say and this produced a slightly better fit as a result, and when I say fit, we're looking at network performance. So our contingency table fit here, 64%. This was on the spanning tree, and then we have about 69 on the Soplec routine. And the other thing that we're looking at, of course, is our occurrence report. So because the issue here, and this shows clearly what happens when you have this kind of data set, is you're going to have portions of your joint probability distribution that are going to have some sparse cells. So here you can see this is the relationship between caribou number 6 and caribou number 10. Neither of them occur in 2,300 of those squares. They co-occur in 13. And then number 10, number 10 occurs in 7 cells that 6 doesn't, and 6 occurs in 2 cells that number 10 doesn't. So I had several hundred of these situations. And now I can actually influence that by, say, increasing or decreasing my cell size. So if I make the cells half the size, I get 4 times as many cells. All of these sample sizes go up. The trick is that the smaller the cell, as you can imagine, the less likely you are to have 2 different caribou in the same cell. So if you make the cells really small, basically all the spatial information on the relationship between the caribou start to disappear. So it's a bit of you have to dial it to figure out which is the right grid cell to capture the spatial information and not lose it. So this is something to play with. In the end, the results were fairly robust, which was good. The other thing that we can do is around variable clustering. So I wasn't just obviously interested in which caribou was most related to the caribou beside it, but really what the evidence was for the spatial separation of groups of caribou. And so variable clustering is another thing I could do, and because each caribou in this situation is a variable. So many of you are familiar with that. So basically the minimum number of clusters you can get is limited by the connectedness of the network, obviously, but you can dial that up and look at higher numbers of clusters and see how they start to fall out on the landscape and see if they make some kind of intuitive sense. So we played with that a bit as well. So once I had once I'd done the clustering and assigned each caribou to a cluster, I could assign each location of each caribou to a cluster. And what I've done is simply colored up each one of the locations according to cluster membership. And the gray underneath are the polygons that I showed earlier, which were how we've been managing them. So the first thing is we're obviously getting a very different answer than what was initially proposed by the researchers, because they're not obviously falling out along the 60th parallel. And we have this one big blob here, so they're actually spanning quite a few of our ranges, but there is some distinctive portions falling out. Now, the one thing that you obviously have to be careful with here is that you need to be confident that you have fairly equal sampling across your sample size, across your study area. Because obviously, if you're flying a bunch of helicopters over here, but you're not flying them here, then you're going to have clustering that represents your sampling rather than the ecological relationships amongst your animals. So it was through looking at initial collaring locations and the distribution of those to make sure that they were equally distributed, and also talking to the original researchers in many of these study areas, because I'm not working in all these areas, to be confident that they have flown these areas and there are no caribou there. So that's one of the tricky things. The other thing too is that we do have some edge effects. So out here, for instance, I'm not convinced this is a separate cluster, but I think it's just because we haven't done enough sampling farther north, and that eventually maybe this will merge with this one. I don't know. The other thing too is that there are some differences, but fairly minor, between some of the different different choices of parameters. The colors aren't identical here, but the main difference here is that we had another cluster. This came out as a separate cluster than this when we ran that routine. So we are getting slightly different answers. So a lot of back and forth with the researchers, a lot of turning the dials to take a look at what makes the most sense. And in the end, we came up with this final version where we did use the 10 kilometer square grid, just a binary discretization. We stuck with the maximum weight spanning tree, just with the minimum number of clusters. So it's not a particularly sophisticated analysis compared to some of the things you can do with BayesiaLab. But we did adjust the structural coefficient, which basically increases the connectedness of the network. And the reason why we did that is that because we had this little foot here, and we had some other information that suggested that these animals should really be grouped in with these. And by making that adjustment in the structural coefficient, it basically absorbed these points into this without changing in the structure anywhere else. So we were fairly happy. So it's tricky because, of course, there's a lot of dials here, and you run the risk of basically fitting it to the answer that you want. But still, I think it's a demonstration that we can use a more objective method of defining the spatial structure amongst the population. And it's been quite well received. And most of the criticism that has come back has been around making sure that obviously there's some nice equal distribution around the sampling. But it's worked out quite well. Going back into BayesiaLab and just mapping out what this looks like, again, not spatially, but just coloring up each one of the clusters according to the cluster that they're in. And also, this is the, what did I do here? Normalized mean is what I've used for the size of each one of the nodes, which in this case reflects basically sample size. So you can see there's quite a bit of difference in the number of locations that were collected on each animal, but it really gives you a quick visualization of where maybe the sampling was relatively poor, and in some of the clusters where we actually, like this green, where we had quite a number of samples for each one of those caribou. And then you can see all the ones that didn't cluster are these tiny little circles here, and really represents the fact that it's not that they're not off by themselves. There's just insufficient data to be able to resolve them into one of these clusters. So we were pretty happy about this, and I'm excited to be able to integrate this with some of the features and the new features in BayesiaLab 7 that Lionel was talking about yesterday, because of course I have to go back and forth between my GIS and BayesiaLab to do all this mapping, but now that we have some integration of Google Earth, I should be able to do more of that in the program itself. As I said, there's lots of dials to turn here, sensitive spatial sampling, and then a number of places where we can adjust things based on how we're specifying the analysis, can change things, how we can change the results that we get. But turning these dials and seeing how robust the final answers are to some of these dials gives us some confidence in what we're seeing. The other thing too, actually, just yesterday at 3 o'clock when we were having coffee here, I got an email from a colleague who he works about here, and he has been talking to the elders in the First Nations community in this area. He showed the map, and they were quite happy that it very much lines up with their traditional knowledge of how they think that caribou follow the land base, follow the landscape. And we've also got some corroborating evidence from genetics as well on some of the spatial structuring. So we've got some good backup, independent lines of evidence that we're getting closer to the right answer here. Okay, that's all I wanted to talk about on that. Just a quick preview of where I'd like to go next. So this is pretty interesting. We've got a new source of data, and they're all related right here. There's this little box here, and this is a remote camera. So there's a lot of these remote wildlife cameras that are showing up. So you can buy these things for a few $100s, and you can put the batteries in them in a big SD card and leave it out there for a year. And it's a motion-sensitive camera with an infrared flash, so it can capture images during the day and during the night. And so the researchers, this is the first week in November, by the way. And so right at the beginning of winter, the cameras went out, actually almost 2 years ago was when this photo was taken. And we have an array of 85 cameras throughout this one range in northern Canada. And these cameras are great, but they're different. There's a different kind of data, obviously. So you don't chase down the animals, which is good. We actually have to fly out to deploy the cameras. So it costs probably $50,000 to $60,000 in helicopter time just to put out the 85 cameras because the access is poor. But once they're out, you only have to go out once a year and change those. And obviously, it's safer for the researchers. It's safer for the animals to do that. And the other thing, of course, is that you can not just capture data on caribou, but you're capturing data on basically all of the animals that are using that area. The downside is you can't individually identify them. So you see caribou, you don't necessarily see you don't know if it's the same caribou, obviously, except if they have collars on them. And we have captured collars in some of these photos, so we know who they are. And then you get a grad student go through many, many photos and determine, because sometimes if you have wolves walking down here, and we might have 2 or 3 cameras, you want to figure out if this is one observation of 2 wolves or 3 observations of at 3 different times. So you have to do some work to figure that out. So yeah, moose, elk, caribou, researchers, caribou. I think this is a little wolverine. I think. Grizzly bear, bison. These are actually feral bison. People, there used to be a bison farm in the area, and it closed down, and they just released the bison, and now they're in the wild. So they want to remove those because they're feral. This is a lynx, and wolves, sandhill cranes, and another caribou. So it's quite an exciting data set, and the kinds of questions that we're asking here are, what are the influences of snow condition on habitat type and on the state of forest regeneration, on the probability that we get higher encounter rates between wolves and caribou, because wolves are the main predation source for caribou. And so by looking at this, we'll have another number of predictor variables and data from all these cameras, and it gives us an opportunity to really get at another entirely different perspective on the land base. Should I show another video, Stefan? Is there another?
Please, yes.
Oh, okay, one more video. This gives us just another perspective on the capture here. Sorry. There we go. So this is a view, obviously, from the outside. You can see the researcher came out of the helicopter. They come very, very close in. Obviously, you don't want to run the animals too long to exhaust them. And once they're tangled, that's it. So then you can see that their friends don't even, they just go back to feeding and kind of look on and say, well, this is interesting, while they're processing the animals. So yeah, she simply just sits on the animal so it doesn't move. The hooves are hobbled. Now they're going to do the release. So obviously, the most dangerous time for the researchers is when they're being released, because the antlers can come up and but again, you can see that She doesn't quite know what's going on, but she doesn't seem too particularly concerned. And you can see the radio collar. There you go. That's it. Thank you.
All right.